Despite decades of research, memory safety bugs are still a problem. Microsoft, for example, estimates that 70% of the vulnerabilities they patch have a memory safety bug as their root cause. There are two fundamental problems here. First, by debugging or testing a program, you can ensure that it works well enough for normal use, but these methods are not suited to find small bugs in corner cases. The second problem is that modern hardware and C and C++ only provide coarse-grained memory protection. This means that these small bugs quickly escalate to serious security vulnerabilities. We address the first problem with more rigorous engineering methods. We do this for the development of hardware. In particular, we are replacing Prose architecture specifications with formal architecture models. An architecture describes the hardware-software interface. So it describes the behavior that software can depend on and the behavior that an implementation needs to provide. By replacing a Prose specification with a formal model, there are some immediate benefits. The model is parsed and type-checked, which catches some easy-to-make mistakes, and it is executable. So you can run software directly on the specification, and you can easily test hardware implementations against this specification. The formal architecture models also allow for formal verification. We define some security properties that capture the guarantees that the architecture tries to provide, and we mathematically proved that the architecture satisfies these security properties. The mathematical proof gives a high confidence that the architecture indeed satisfies them, even in corner cases that would be difficult to test. To increase our confidence even more, we verified our proofs in Isabelle, an automated proof assistant. We do this for CHERI. CHERI is a processor architecture with new security mechanisms, and it addresses the second fundamental problem. CHERI adds fine-grained memory protection and scalable software compartmentalisation. It achieves this by extending existing architectures with a capability system. The prototype of CHERI is CHERI MIPS. So the main artifact here is its instruction set architecture, and it has a hardware implementation that runs on FPGAs. So you see an old picture here on the left. And there is a software stack, including LLVM and FreeBSD, that are adapted to make use of CHERI's new security mechanisms. There are also other versions of CHERI. CHERI RISC-V and CHERI ARM are under development. So CHERI ARM is developed in a project called Morello, which has significant funding from the UK government and from ARM. And here the goal is to produce an industrial prototype of CHERI. And we hope that CHERI security mechanisms are integrated in ARM's main processors. So in our paper, we apply the rigorous engineering methods to CHERI MIPS, but at the moment we're also applying them to the development of CHERI ARM. So CHERI's capability system adds fine-grained memory protection and scalable software compartmentalisation. Fine-grained memory protection is best explained by comparing it to current C implementations. So on the left side you see a program and it has an information leak. And that's because pointers are typically compiled to just machine addresses. So here you have a pointer p that originally pointed to x, but then it was increased by 1, and because x is next to the secret key in the memory, it now points to the secret key. So the printf statement simply loads the secret key and displays it. With CHERI, on the other hand, pointers can be compiled to capabilities. And a capability has an address, so it still points to a memory location, but it also has bounds information. So the pointer p is compiled to a capability that has a base that is the start of the memory region of x and a length that's accordingly. And whenever you try to use a capability with an address that points outside its bound, the hardware will trap. So here printf will not leak the secret key because the hardware will trap. So far that sounds like a fat pointer approach, but there's the main difference with the capability system is that a capability system enforces the integrity of capabilities. So you cannot just change the bounds of a capability. And to see whether a capability is still valid or not, CHERI adds tags. So tags to the memory and tags to registers. and if you try to overwrite the byte representation of a capability, this tag is automatically cleared. You can manipulate capabilities with new instructions that CHERI adds. Those instructions, for example, change the address or decrease the bounds or remove permissions, but it's crucial to the design that there are no instructions that increase the bounds or add new permissions. You can use this capability mechanism to compartmentalize software. So you give compartment A capability to a certain region of memory, and you don't give it any other capabilities. And that means that whenever it tries to access other memory, the hardware will trap. So this compartment A can only access its own memory. And you can do the same with another compartment, and if you set them up with isolated regions of memory, they can't touch each other's memory. These compartments can delegate some of their memory. So by copying their own capability, restricting the copy and sending that to the other compartment, you can end up in a situation where they have some private memory and they share control over a shared region. Then, to allow mutually untrusting compartments to cooperate, CHERI has two new mechanisms. One is that you can seal a capability. So a sealed capability is no longer useful to access memory. You can no longer use it for that, but you can invoke it. And if you invoke a sealed capability, that unseals it, but it also atomically jumps to the address it points to. So that means if you set up compartment A and B correctly, you can give them each other sealed capability, and if they invoke it, you jump to an entry point of the other compartment. So this brings us to our first contribution, the formal architecture models. To contrast that with traditional engineering, those are centered around Prose architecture descriptions. So if you want to know whether your hardware implementation satisfies this specification, then you need to write a handwritten test suite. And your software stack cannot run on Prose, so you need to run it directly on the hardware implementation. So what we did is we replaced the Prose specification with a formal model. And it's important to note that there's no formal background necessary for this. The engineers that would otherwise write the Prose specification now develop the formal architecture model. The formal architecture model is executable. So now you can test the hardware implementation by just comparing traces with the architecture model. And you can run software directly on top of the architecture. This has really helped with experimenting with new design ideas, because every change in the architecture has effects on the implementation and the software stack. They might not be viable to implement, it might hurt performance, or it might not be useful. And because the architecture model is executable, you can quickly find out. This is an example of the formal architecture specification. This is the cload instruction that uses a capability to load data from memory. It's not necessarily to understand this in detail. I'm just briefly describing it. Describes some conditions when the hardware will trap. It also specifies the order, which exception has priority. And it more or less is similar to the pseudocode. It just has some more type annotations. Then our second contribution are the formal security properties. So CHERI's design, the capability system has some key properties. For example, monotonicity. That means that you cannot increase bounds and you cannot increase its permissions. The documentation specifies that, but it doesn't precisely define what it means to make a capability bigger. For example, it doesn't say whether sealing and unsealing is regarded as narrowing or increasing the rights. It also says this monotonicity does not always need to hold, and it continues that if it does not hold, then controls transfer to codes trusted to utilize and gaining rights appropriately. But it doesn't say whether we trust the code because it's trustworthy or because we have to trust it, so we have no other choice. So what we did is we cleared these confusions, these ambiguities, by defining formal security properties. And our focus is on reasoning about arbitrary code. So to see whether our security properties are strong enough to be actually useful, we defined a simple compartmentalisation scenario, and we would like to prove it correct. So we took some intermediate steps, And to know what a compartment can do, you have to know which capabilities it can access or construct, because those allow it to access memory. And to be able to characterize those capabilities, we defined an abstraction of CHERI MIPS. So this abstraction only keeps the memory accesses and capability manipulations and abstracts away from all the rest of the architecture. And then our final contribution is that we related all those with mathematical proof. So we proved that the architecture is correctly abstracted by our abstraction, and we proved the characterization in the abstraction, and finally we proved the compartmentalization scenario correct. So as I said, the abstraction only keeps memory accesses and capability manipulations, and it also keeps hardware exceptions. So instead of executing an instruction, you now perform abstract actions, one of those 9 types. And then we connect the architecture to these abstract actions by mapping the instructions. So the add instruction, for example, does not do any memory accesses or capability manipulations. So we map to the empty set. The instruction that decreases permission is mapped to the action that restricts capabilities, and so is the instruction that decreases the bounds. Conditional instructions can map conditionally to abstract actions, and then we continue and we do this for all the instructions in CHERI MIPS. And then we define security properties for each action. So here as an example, I'm defining the security property for storing data. We start with just a technical assumption. Then we take a step and a certain number of actions happen. And we assume that this keeps the protection domain. So we're not transitioning to another compartment. We also assume that storing data is one of the actions that were performed. And there's some information associated with that, the address and the length of the access, and also the capability that is used as authority. Then we require that the capability that was used as authority is valid, has a tag, it's not sealed, and it has to permit store permission. Then a well-formness requirement, and we also require that the memory segment we're storing to is included in the bounds of the capability. And here we have to translate all the addresses because the capability is to virtual memory, not to physical memory. Finally, because we're writing bytes, we have to clear the tag if there's a capability there, or we can also leave the capability completely intact. And we give this a name. So we defined a property like this for all of the abstract actions, and together they form the abstraction. Then we use this to reason about compartments. So we want to know which capabilities a compartment can reach if it's allowed to execute arbitrary code up until it transitions to another compartment. So the base case is that capabilities in registers are accessible, and then if a capability is reachable, you can use it to load another capability or to seal or unseal another capability. And as I said, we only do this up to a domain transition. So we deliberately do not include invocations and exceptions here. Then one of our main results is a theorem about reachable capabilities. We again assume that state is valid, and we assume that none of our reachable capabilities has system register access. And this is a very important assumption that is missing from all the Prose definitions. Then we take a future state and we assume that it does not cross the domain. And then our conclusion is that this set is monotonic. So if a capability is reachable in a future state, it was already reachable in your starting state. Then finally, we are going to look at our simple compartmentalization scenario. Here we have one compartment and we granted access to certain addresses. We defined a simple assumption on the capabilities that are in memory at those addresses. And then our requirement is that it cannot touch any other memory. So we proved it, and the previous theorem was a crucial part of that proof. So to conclude, we show how to apply more rigorous engineering methods to the development of hardware. And these are centered around replacing a Prose specification with a formal architecture model. There's some immediate benefits here. For example, the formal architecture is executable, and it allows for formal verification. So here we cleared up some confusion about the security guarantees of CHERI MIPS by defining formal security properties, and we mathematically proved that the architecture satisfies these properties. We did this for CHERI MIPS, but the ideas are portable. We are currently doing some work for CHERI ARM, and we're using the same rigorous engineering methods here.